All right, thanks a lot for joining us this afternoon for our talk about common myths in stream processing and an introduction into Apache Flink. My name is Robert, this is Ufuk. We are both committers and PMC members at the Apache Flink project. We are employed at Data Artisans, a company founded by the original creators of Apache Flink. We all met each other back in the university. It was back then a research project that we turned into a startup. We are also offering a platform called the Data Artisans platform that is basically a distribution of Flink, including paid support. So if you need to call somebody in the night because Flink is not working, this is where you can sign up. In this talk, we are going to do a quick introduction into Apache Flink and the stream processing space in general to have a common understanding of the terms that we are going to use in the part where we are talking about the 4 most common myths in stream processing that we are often hearing. And the objective of this talk is to clarify these misunderstandings about stream processing in general by giving an explanation. And then we'll conclude with a bunch of numbers about the Flink community and also some big users of Flink that are using the system in production. So let's get started with an introduction into stream processing. So who of you has heard about Apache Flink before? Cool, that's a large number. And who is using Flink in a POC or in production? Okay, that's like 5, 6, I don't know, people. I hope we can increase this number after this talk. So as 50% of the people here know, Apache Flink is an open source stream processing framework developed at the Apache Software Foundation by around 25 committers and a very large community of contributors consisting of different companies. We are focusing on low latency processing while still allowing users to have very high throughput of their data. We also provide abstractions for managed state in the system to allow more advanced applications and use cases. And the system is like Spark and Hadoop and all the other systems distributed, so you can use it on commodity hardware at scale. It's fault tolerant. So that is the very, very basic high-level overview of Apache Flink. And now I will talk a bit about what is stream processing actually. And for that, I'm going to use a very simple example, which is log analysis. Something I guess that is one of the most basic big data Hadoop use cases from the past. So imagine you have a bunch of web servers, and every time somebody is, I don't know, clicking in your shop, it's generating an event in a log file. Then you have some periodic service that is collecting these logs and putting them into HDFS. And from there, or it can be any other distributed file system. And then you have, I don't know, an implementation of a batch job in Spark or Hadoop that is periodically, like every 4 hours or so, reading your data, building some statistics like aggregations and so on, and then putting it somewhere like Cassandra or Elasticsearch, where you can access a dashboard to see the numbers. I think that's a traditional approach for analyzing data to understand the user behavior of your website and so on. Let's look a bit at latency of this implementation. So how long does it take from the event being generated on the web server, so the user clicking on something and the web server logging a line in the log, until you get the fresh numbers in your dashboard? So if you're running this batch job every 2 hours, you have a latency of 2 hours until you know what is currently happening in my web store. So if you're doing data processing without a stream processor, you're usually in the latency area of hours. There are other systems that integrate this periodic scheduling approach into the engine. I think the most prominent one is Apache Spark, with a micro-batching model for stream processing. So it's a batch engine, and they just periodically start batches. They collect data and start batches to process data. And from the outside, it looks like a stream processor. With that approach, you can get into the minutes latency and even into the seconds latency area. It depends, of course, on your workload and your cluster size and so on, how fast you can schedule the batches in Spark. But if you want to go down to the milliseconds area or the sub-second, small seconds area, then you need to use a stream processor, a system that is continuously reading your data, continuously receiving events, and continuously updating the dashboard. So the downsides of doing stream processing with a batch engine is that you have very high latency, you have delayed results in the area of hours or days. You have a very complex architecture because you need some system to periodically schedule these jobs, to automatically load the log files. You need to make sure that you're not loading the files multiple times if there's an issue with the loading. You need to maintain the batch processor or the batch jobs or the Hive jobs. And if you're using the Lambda architecture, you also need to maintain the stream processor and Kafka. So that is a lot of maintenance overhead. It costs money, you need engineers, something you want to avoid. There are also technical issues like how do you handle back pressure when there are load spikes. So yeah, I think it makes sense to look if there's an easier way of processing data that is generated in a continuous streaming fashion. And that is what streaming architectures are doing. You have your web servers, and instead of writing the events to local text files, you're sending these events immediately to Kafka or to Kinesis or to some other message bus system. And the stream processor is continuously reading the data from this message bus and analyzing it. So once a user is doing an action on your website, you almost immediately see an update in your serving layer. So you can just implement like a time window where you're collecting data of the last n seconds, and every 5 seconds you're updating your aggregations in the downstream system like Elasticsearch to show it in Kibana. So that is what stream processing is about. Real-world data is usually produced in a continuous fashion. Users are always producing data continuously. There's no such thing as oh, look, there's this 5 terabyte file, I need to process it now. This 5 terabyte file is continuously growing as users are active on their apps or on their websites or in your bank or whatever. And new systems like Flink and Kafka are embracing this streaming nature of your data. They are continuously analyzing it. So how do you implement something? How do you implement a use case using a stream processor? At a very high level logical view, you have events coming in. These at the very top left, these blue boxes are events. You have some custom code where you transform these events into the yellow boxes which are transformed. So if you do a very simple ETL use case where you're just extracting some data, this is sufficient. This is something that you I don't know, can do for quite a while with Storm in the last few years. And these systems like Flink and Storm, they're also distributing this workload in the cluster. So the lower left picture shows you how this is executed in a distributed engine. Then multiple instances of your code are running, your data is shuffled across the cluster to allow you to scale up. But what happens if you want to do something more involved? So if you want to do like counting, or if you want to build session windows, so if you want to analyze a user activity stream, so from the point where the user is logging in into your website, is performing some activity and then logging out again. If you want to analyze that session, you need to have some local state in your operator that stores all these events that the user has been doing in his session. And therefore, modern stream processors like Apache Flink provide stateful streaming. And the system is managing that state for you. So you can register that state with the engine, and the engine is taking care of backing it up periodically and using that backup to restore it in case of a failure. It also allows you to do snapshots of the time. So if you you can do like a snapshot every morning, and when you detect that there was a bug in your system, you can just roll back to an older snapshot and do reprocessing. It also allows you to version your state and also to do upgrades of the system, of your hardware, of your application. So I think it's a quite useful concept to make the system, the streaming system, aware that you have state, because it allows new use cases and more advanced applications like session windowing or complex event processing or SQL or just aggregations on streams. I usually don't show code on slides, but in this case it's very few lines. So this is actually the most simple state abstraction in Flink, the value state. You can just use any Java type with it. Here it's just a long for counting the number of elements that you've seen in your stream, and it's just updating the count by 1 on every record it receives. And the cool thing about this value state is that it allows you to back up the count, and it provides you exactly one semantics for that state. So even if the system fails and it needs to reprocess, it still ensures that the counter is always correct. And it does this by having the offset of the Kafka topic, for example, in sync with your counter. And it allows you to do all the other steps that I mentioned earlier, like rollback and so on. Another very important ingredient or building block for allowing modern applications on a stream processor is the support for event time. So imagine you have, in this example, these web servers, and these web servers are located in different data centers, and the clocks are slightly off in these data centers, and it takes a while for the data, for the events, to travel to your processing cluster. And the problem is that your data arrives out of order in the stream processor. It doesn't arrive at the time when the user clicked. It can have delays. And to work around that, Flink is aware of the time of the event. So in the API, there's a call to extract the event time. So I don't know, if your mobile phone is generating an event, it attaches a timestamp to it. If your mobile phone is then on the airplane and then gets back to the network, it will send all the events to the stream processor. So the event has a delay of 2 hours, but the stream processor is still able to correctly process your data by having this event time awareness. And another very important part of this event time awareness is also that it has a feature called watermarks to track this event time. So if you're doing reprocessing, I said you can do rollbacks with a state management. So if you're doing reprocessing, the system can process your 2-week-old data and still build exactly the same windows for your sessions and so on based on the event time. That is a very powerful feature for replacing existing batch infrastructures with a stream processor. And to wrap up my introduction to stream processing, I would like to quickly have a look at the Apache Flink stack to show you what you're getting when you're downloading the latest Flink 1.2 release on our website. So at the very bottom are the different deployment layers. You can deploy it onto Hadoop Yarn. Since Flink 1.2, you can deploy it on Mesos. We have Docker images in the Flink source code, and we also provide Docker images in the Docker Hub. There's also a standalone cluster mode that allows you to just use bash scripts to start Flink, but there's also you can also integrate this with a custom system for deployment. And there's a local mode to just run Flink on one machine. It will execute exactly the same code as it would on the cluster. This is extremely powerful if you want to attach a debugger, if you want to see the log outputs locally, if you want to understand what's going on in your application. Then there's the core engine that is like doing all the network transfer, the state handling, the event time handling. And on top of that are 2 APIs, the dataset API for batch processing and the data stream API for stream processing in Java and Scala. And on top of that API, we have some specialized APIs for specific use cases like complex event processing, SQL on streams. So since Flink 1.2, you can build windows using the table API of Flink at a very high level. It's very intuitive to use it. And for Flink 1.3, we're working on a new abstraction for doing event time window processing using SQL. So there are lots of interesting things to explore when you're interested in Flink. And now I would like to hand over to Ufuk to talk about some common misconceptions about stream processing and how we want to clarify or answer these misconceptions.
Yeah, cool, thanks for the intro. Hi everyone, I'm Ufuk, as Robert said earlier. And to just give some background to how we came up with this talk. So there's this TV show, I think on Discovery Channel or something. It's called Mythbusters. And these guys would walk around and look at everyday myths and clarify them. So we try to do the same thing for streaming here today. And I will talk about 4 such myths. And the first one is that streaming is approximate. And this goes pretty far back. So sorry, there are also some variations to this. So for example, most prominently that you have to combine stream processors with a batch processing system like Hadoop or Spark. And this actually goes back to the very early days of stream processing when the Lambda architecture was proposed. So the idea here is that you have on the left side some events that you capture and you feed them into 2 separate systems at the same time. On the upper half, that will be the batch system where you periodically schedule your batch job. And on the lower half would be the streaming job. And in the end, when you want to build your dashboard or whatever, you have to combine both the output of both systems. And the idea for this actually back in the day was that the batch system is responsible for accurate results on very high throughput input, whereas the stream processor is responsible for the fast results, but it was only approximate. So we don't recommend to use this nowadays. I think in the beginning it was very useful. But it turns out, for the reasons Robert already mentioned, that nowadays you don't need this anymore. So the stream processor can give you both accurate results and work on very high throughput data volumes. So the good thing is that we don't hear this too often these days. And in the next 2 myths, I will probably clarify how you get accurate results and that you can also work on high data volumes. Yeah, the next myth, and it's touching on this accuracy of the stream processor, is that exactly once is not possible. Variations to this is that exactly once is not needed, or that it requires significant performance trade-offs. So the question is actually, to start with, what is exactly once? Robert already mentioned it. If you have your stateful streaming pipeline and you want to keep track of counts, for example, you would use manage state in Flink to keep track of this. And the question now is, what happens to the state when a failure occurs? And what exactly once semantics give you is that the state is always as if no failure occurred. And this is in contrast to, for example, at least once, where in failure scenarios, duplicates, for example, could occur. And traditionally, there has been a lot of confusion around this term exactly once, because it was not used very precisely in the stream processing space. So we would have to differentiate between exactly one state. This is what Flink gives you, and this is very, very, very much possible. And exactly once delivery, which is actually not possible in general to guarantee. And this goes really back to the very early days of streaming. For example, Storm in this first version also talked about at least once, but was talking about delivery. And then when later systems came around, like Apache Samza, it was also talking about it at least once, but it was referring to state. So we really have to be precise on what we talk about. And when you talk about state semantics, then you can really get exactly once. So now we want to look at how to actually achieve this. And we look at the example of Flink Checkpoints. So what you have here is, again, a very simplified visualization of how your stream processor could work. You have a task, and you have the colored boxes, which are records that are being processed. And what we do in Flink, at least, is we inject so-called checkpoint barriers with the data flow. They flow in order with all your records. And as soon as a task receives the barriers from its incoming from upstream operators, it can checkpoint the state. And the cool thing is that checkpointing this can be done asynchronously, so it works really well with also with very, very large state sizes. And when the failure occurs, you can roll back your state for all operators of your pipeline back to a consistent snapshot that you took, and this way you get the exactly once semantics. And another cool thing is that the same mechanism actually can double as a transaction coordination mechanism with external systems. So previously I said exactly once delivery is not possible in general, but if you want to move state from Flink to another system, you want this, you want exactly once delivery. In general, this is not possible, but when you integrate your sync operators with Flink, we can do this. For example, if you do a pipeline like read from Kafka, do your processing in Flink and write out to HDFS again, this is doable because we integrate with the file system. And actually, what's also very cool about the checkpointing mechanism is that it triples also as a state management mechanism. You can trigger the checkpoints and write them out to very long-term storage and go back in time and version your code and state consistently. So we believe that this is very powerful in practice, where you are continuously like changing your code and going back in time to check bugs and stuff like this. Yeah, the next myth is about throughput and latency. Was also present in the early days when the Lambda architecture was proposed, and the idea was that low latency systems cannot support high throughput, or that mini batch systems have better throughput than record at a time systems. And here again, we have to clarify some terms. So the two terms are batching and buffering. Batching is treating a stream of events as a sequence of small batches. So for example, what Robert showed in the very beginning, where you would do this manually with Hadoop, for example, or when you use Spark, and Spark does it for you internally with the micro batches. So this is batching, and buffering is usually a performance optimization that should be very opaque to the user. So you should not be aware of this. And the myth is now that only batching can get you high throughput, whereas what actually gets you like good performance is buffering. And really, every system does this. If you think about your operating system, before writing out stuff to a disk, it will first buffer stuff in memory and only flush it out when it has accumulated enough data. And this is also what Flink is doing. So you don't actually operate record at a time in the engine, but it's still very powerful to operate on the API level as if you were operating a record at a time. And a well-engineered system actually should, the performance of a well-engineered system should be dictated by the network, because in the end, this is what dictates like what latency and throughput you can get, and you want to buffer only as much as the network allows you. So coming to the very last myth in this talk is that streaming is only for real time. So many people think that, okay, I don't have a low latency use case, and therefore I don't need streaming at all. We believe that this is also not true, because most data sets that you encounter in practice are actually unbounded in nature. As Robert said with the web server logs, these are produced continuously. And in this case, doing batching is not an accurate computational model, because you split up your data in this files, for example, for each day, and you push out very interesting questions like what happens with the data that lives in the boundary of your batches. So if you want to track a session in your logs that goes across a day, but you only have files per day, how do you do this? So usually what you do when you use a batch processor is you just ignore it. So it's someone else's problem. And the good thing about modern day stream processors is that they give you the right primitives to deal with this. So the primitives for time to do this grouping of data by time inside of the system and not outside of it. And the fact that this is low latency is actually just the icing on the cake. So this is not what it's all about, but this is just a cool feature. So looking at these 4 points, we realized that like every day they become less and less prevalent. We believe that this is a good thing. And we believe that streaming is a very powerful model to do this kind of processing on continuously generated data sets. And the ideas for this have been around like a long time, but what now really enables this takeoff is this combination of working low latency on high volume throughput, high volume streams in an accurate way. And that's why we believe that everyone should actually do this way.
Yeah, thank you, Ufuk. So to conclude our talk, I would like to quickly shed some light on one of the most important aspects of an open source project, and that is the community. It's sometimes hard to measure or qualify the community size and the community health, but we've got some numbers to look at. So the global meetup groups that are spread over almost all continents have almost 20,000 members right now, and it's steadily increasing. Also, the number of individual contributors to our code base is approaching 300. So in December last year, it was at 250. I believe it's around 300 now. And also the stars on GitHub and the forks on GitHub are constantly going up. And one driver for this big interest for people to contribute and to collaborate with us is the companies that are using Flink in production. So since we're in Germany, I have to mention Zalando, one of the largest e-commerce companies in Europe. And they are using Flink for real-time business process monitoring. King.com, the company behind all those smartphone games like Candy Crush Saga, they are processing billions of events with Flink. The Alibaba Group, I think the world's largest retailer, the Amazon of China, they actually forked Flink into a system called Blink over a year ago, and they were using it in production on a cluster of more than 1,000 machines to optimize their search ranking in real time. And they are currently, or over the last year actually, they are working with the Flink community to contribute back everything they did to operate Flink at such a large scale. So we are working on an effort called Flip 6, so the Flink improvement proposal number 6, to rework the whole cluster deployment model to have nicer support for Kubernetes and Docker and all these modern deployment models. And they're also collaborating a lot with us on the SQL side. So as I've mentioned earlier, Flink provides support for SQL on streams. And they are pushing really hard. They have an entire team working on the SQL side of Flink, and they're already using it in production, so they provide a lot of experience for the Flink community to contribute these changes back to the open source. Uber is also collaborating with the Flink community on SQL. So there's quite some big names behind our SQL efforts, and I believe that SQL will be a really big topic later this year. Bouygues Telecom is the third largest mobile provider in France. They've been the first production user of Flink in production. They have 30 Flink applications running in production, processing more than 2 terabytes daily. I believe this number is increasing. So last year at Flink Forward in Berlin, they had a slide with this picture of their network operations center, and the dashboard that you're seeing in the back of the room, that is continuously updated and generated by a Flink application or by a bunch of Flink jobs, which is for me as a developer of the system quite nice to know that this big room, probably full with people 24/7, is using data processed by Flink. So if you want to learn more about these users, you can look at the Flink website, and we're organizing conferences around the world. So next week we're organizing Flink Forward San Francisco for the first time, and later this year in September we're organizing Flink Forward in Berlin. So since you're probably based in Europe, you can just come over and learn more about Apache Flink. It's a 2-day conference including training. You can also learn more about Flink at this conference tomorrow. Our colleague Till will give a talk about complex event processing with Apache Flink and how we plan to unify this with our SQL efforts. So this will allow to do a lot of streaming use cases without writing a single line of code in the long run. And I think also complex event processing is a quite interesting topic that hasn't entered yet the open source world to the extent it should. We're also hiring, so if you're interested in working on cool open source technology in Germany, particularly in Berlin, talk to us. And if you have any questions, please raise your hand. We are more than happy to talk about more myths about stream processing and tell you what we're thinking about this. And of course, Flink questions in general. We also have some Flink stickers here. If you want, just come after the talk. We can give them out. So are there any questions? Yes?
Could you briefly do some comparison to, for example, Apache Spark, other frameworks?
Okay, so the question is how Flink compares to Apache Spark and other frameworks. So concerning Apache Spark, as I said in my talk already, Apache Spark at its core is a batch engine and a batch runtime. And they are using this micro-batching approach for providing streaming semantics, or that it feels like a streaming system, but behind the scenes it's still a batch processor. It means that you have higher latency, and it also means that it's much harder to implement use cases like session windows, because the windowing is based on these micro batches in Apache Spark, and Flink, since it's continuously running and continuously processing your data, it's much easier for Flink to efficiently do session windowing or time windows in Flink. And like features like event time, which are, in my opinion, essential to do stream processing, are only available in this structured streaming that Spark is doing. But I'm not 100% sure. I think it's still in beta and still in development. So you cannot implement something yourself in Java using event time. And if you just talk to one of our production users and ask them about event time, they'll give you a great testimonial about how cool this feature is to reprocess your data from the past.
So you think that the Flink is more mature than Spark in this aspect?
I would say that I haven't attended the talk about Spark streaming that was here before lunch, but I think that's what we are hearing about Spark streaming, is that it's sometimes hard to use it in production at scale. But maybe we are the wrong persons to ask, because obviously if people are unhappy with Spark streaming, they're looking for alternative, and we are the alternative. I guess if you're asking the Spark committers, they have a different answer, and I'm sure they are working on this. But we are, like the Flink community is really dedicated to the streaming space. We are only working on streaming stuff, like the complex event processing, SQL on streams, machine learning on streams, batch processing on streams. So I think there are a lot of interesting things in the pipeline later for this year. Yeah. And other stream processors, I'm not hearing much about them. So Storm is still around. Does it have exactly once guarantees?
I think so by now, yes.
Yeah, by now, yeah. Yeah. But I would really recommend to implement your use cases on Flink and Storm, do like a little proof of concept and run some numbers, check on your hardware what performs better, what feels better for you. And I'm pretty confident that Flink will be the choice then, because it's really easy to use and nice to deploy. So just try it out and you'll see yourself. Yes? Yeah.
And I ran a test with the one T. Roman presented. I also noticed some attempts to integrate other CEPs with Flink.
Yes.
Are you backing them up? Or what is your strategy about CEP?
So since it's an open source project, we are completely open to other systems using, or other CEP libraries using Flink. And there is indeed a CEP library, I think it's called CIDI. And there is a pull request against the Flink repository that is doing that implementation. So if you're interested in that, you can just use this pull request. The reason why we're not merging it is that there is another project called Apache here for these kinds of integrations. So I've asked the guy who opened the pull request to contribute City to Apache here. So we are supporting them, and I would be happy to see users using City and Flink. No. Yes?
I heard that Flink is the favorite runner for Beam, and I saw a while ago that there's a plan to make them syntactically identical. So is that a real thing that's happening between Flink and Beam?
So Apache Beam is like an API that is independent of the engine. It's mostly developed, or it's out of Google, and they offer to run Beam applications in the Google Cloud using Cloud Data Flow, and many other open source stream processors are implementing a runner for Beam, and I think Apache Flink, so they have this compatibility matrix on their website, and the Flink runner supports most of the features right now. I think it's the recommended way to run Beam in production to use the Flink runner, because you can get all the features like managed state, event time, all the window semantics, all that stuff is doable using Apache Flink on Beam. So it's just an orthogonal effort to our API, and we are supporting the Beam community in integrating with Flink and making sure that everything in Beam works on Flink.
Do you recommend going through that API or using the native Flink?
It depends a bit on what you want to do. If you want to be extremely flexible in the future, then I would recommend Beam. But if you want performance and if you want to use all the features in Flink natively, then I would recommend to use the Flink API. And I also think that the time to implement a streaming application is usually not so much compared to the time you need to spend on to run it on an engine. So in the end, it doesn't matter so much. It's just it is a different way of implementing. It's a different flavor. Yeah. I would try out both, like spend some time to check them out, and yeah.
Okay, Flink is a really great tool, but what would you say about the downside of Flink compared to another tool like Spark or Stateful? In which cases do you not recommend using Flink?
I think we're biased.
Yeah. I don't know. I haven't. I think there's no failed POC that I've worked with where they said in the end, yeah, we don't want to use Flink anymore. I think if you're really purely on batch, and if you don't expect in the foreseeable future to go to use a stream processor, and you have a lot of batch systems, then maybe just stick with Spark or MapReduce. But if you're planning to reduce your latency, or if you're starting from scratch, I would recommend using a stream processor, because that's just more powerful concept-wise, because you can do most of the batch use cases with the stream processor as well. Yeah. Yes?
Thanks a lot for the talk, very nice, and also thanks a lot for expanding the brief.
Thank you.
I want to ask you, what is your magic behind Flink? So what really works? Because many other projects try to achieve the same thing, but they can't.
Yeah. So what's the magic? The magic. I think the magic behind Flink is a very well implemented core engine that. So the checkpointing is very efficient, so it doesn't reduce the latency or the throughput. It is also tunable. You can adopt it to your use case. So if you want latency, if you want to reduce the latency, you can turn a knob. So there are many turning points to configure the system, and yeah, it's just overall well architected to support many use cases. I think that's really the secret.
Time's up, but last question.
Yeah.
Yeah, I hope this can be quick because we're running out of time.
Yeah.
So I'm running an organization with 100 analysts. All those analysts are trained in SQL.
Yeah.
So the greatest hurdle for
tables to streams and from these 100 analysts' way of thinking tables. What's your take on that, and what's your experience?
So as I said, we are putting a lot of effort into SQL, and like SQL on streams, like Hive is for batch SQL, or and Flink is really trying to come up with a good solution for doing SQL on streams. Till is going to talk a bit about this tomorrow, I think, in his talk. And I think this will allow analysts to operate on their streams.
I think that would be the killer, providing appropriate levels of abstraction.
Yes. Yeah. We published a blog post last week about how we want to do SQL on streams. It's called Dynamic Tables. Yeah. It gives you a logical view on the stream.
You can also continue offline.
So thanks a lot for your attention.
Thank you.
We are still here having Flink stickers and answers for you.
Thank you.